Alright, before I show you anything else, look at this. Nobody hacked this password. Nobody cracked it. The website sent it across the network exactly like this. And in the next few minutes, I'm going to show you 3 different ways to find credentials with Wireshark. Then, I'll show you what your network still leaks even when everything says HTTPS. Let's jump in. Real quick before we start, only capture traffic on networks you own or you're authorized to test. Everything you're about to see is happening inside my own lab. Now, the first thing I always do is look for the interface that's actually carrying traffic. See this little graph moving? That's the one I want. Double-click it, and now we're capturing live packets. Honestly, before running any fancy tools, I like to just sit back and watch the traffic for a minute. You'd be surprised how much information is already flying around. For this demo, I'm using DVWA, the damn vulnerable web application. It's running inside my lab, and it's perfect for showing what insecure web traffic actually looks like. Now watch this. I'm going to log in like a completely normal user. Username, admin, password, summer 2026. Nothing special, just a normal login, and we're in. If you were just looking at the browser, everything seems completely normal. But what actually traveled across the network? That's where Wireshark comes in. Right now, Wireshark has been recording every packet since we started capturing. The only thing we need to do now is find the login request. Luckily, that's pretty easy. Whenever you submit a login form, your browser usually sends what's called a POST request. Think of it like a package carrying your login information to the web server. So let's filter for POST requests and see what we get. There it is. That's the login we just submitted. Destination, IP address. Now here's where things get interesting. I'm going to right-click the packet, choose Follow, then HTTP Stream. This reconstructs the entire HTTP conversation between the browser and the server. Take a look at this. At the top, you've got the request itself, the headers, the destination, everything the browser sent. But scroll down just a little bit, and there it is, username, admin. And right underneath it, password, summer 2026. Completely readable, no decoding, no brute force, no password cracking. Wireshark didn't break anything. The website simply sent the credentials exactly like this. And this is exactly why plain HTTP is dangerous. If someone can capture the traffic and the application isn't encrypting the connection, they don't need to hack the login page. The credentials are already sitting in the packet. Now, you might be thinking, nobody still does this anymore. I wish that were true. Older printers, IP cameras, cheap home routers, NAS devices, industrial control systems. I've seen all of them exposing logins over plain HTTP. Not because they were hacked, but because that's simply how they were built. Alright, HTTP isn't the only protocol that can get you into trouble. Let's look at 2 protocols that security people have been trying to kill for years, FTP and Telnet. You'd think they're gone by now, but they're not. I still run into them on older printers, security cameras, switches, industrial equipment, even production systems. And the scary part? They don't even try to hide your credentials. Let's connect to this FTP server. Nothing fancy, just a normal login. Username, MSFadmin. Password, MSFadmin. We're logged in, and now let's see what Wireshark captured. FTP is actually one of the easiest protocols to analyze. Every command gets sent separately. So instead of digging through hundreds of packets, we can filter specifically for the user and pass commands. There it is. usazir msfadmin. And right underneath it, pass msfadmin. Again, completely readable. No encryption, no protection. Now let's make this even easier. Instead of looking at packets one by one, I'll follow the TCP stream. And there it is. The entire conversation. The login, the password, every command I typed. Everything the server responded with. Wireshark rebuilt the whole session for us. Now let's look at something even older, and honestly, even worse. Here's a Telnet server. Same idea. I'll log in just like a normal administrator would. And we're in. Now let's go back to Wireshark. This time, I'll just filter for Telnet traffic. Looks normal so far, but watch what happens when we follow the stream. Seriously, look at this. Every key I pressed, every character, The username, the password, even commands after logging in. It's all right here. That's because Telnet doesn't encrypt anything. It simply sends every keystroke across the network exactly as you type it. If somebody can capture the traffic, they can literally replay your entire session just by reading the packets. Now here's the part that surprises people. This isn't just something you'll find in a lab. I've seen Telnet running on older switches, industrial controllers, security cameras, legacy servers, even production equipment that nobody wanted to touch because it was still working. Old doesn't always mean gone. All right, let's clear up one of the biggest misconceptions I see online. People spot base 64 and immediately assume it's encrypted. It isn't. Let me show you why. Here's a base 64 encoded value. Let's decode it. Username, admin. Now let's do the password. Done. That took, 2 seconds? That's because base 64 isn't encryption. It's just another way of representing text. If you can read the traffic, you can decode base 64 almost instantly. You'll see this in email protocols, basic authentication, older web applications, and a bunch of internal tools. The credentials may look scrambled, but don't let that fool you. Encode doesn't mean encrypted. That's an important difference, and one every security professional should understand. All right, we've seen how plain HTTP can expose credentials, but what happens when everything switches to HTTPS? Most people assume that's the end of the story. Not quite. Let's start a fresh capture and see what actually happens. I'm going to visit a few different websites, example, com, GitHub, Wikipedia, Cloudflare, Ubuntu, Kali, Stack Overflow, and python.org. Nothing unusual, just normal web browsing. Now let's head back to Wireshark. The first filter I'm going to use is simply DNS. Before your browser can connect to any website, it has to ask one simple question: where is this server? That's exactly what DNS does. Right here, you can see both the DNS requests and the responses. Every time I opened one of those websites, my computer had to look up its IP address first. If I only want to see the requests my computer is sending, I can narrow it down even further by filtering out the responses. Now we're only looking at the DNS queries leaving my machine. Let's open one of these packets and expand the queries section. Here's the domain name, example.com. Here's GitHub, and here's Wikipedia. None of this traffic is encrypted. Anyone watching the network can immediately see which domains your device is trying to reach. Now let's look at something else. I'll change the filter to Server Name Indication, or SNI. This shows information exchanged during the TLS handshake, right before the encrypted session begins. Let's open one of these packets, expand the Server Name Indication field, and there it is, github.com. Here's another one, wikipedia.org, and another, example.com. Even though the connection itself is encrypted, the host name is still visible during the handshake. If I scroll through the capture, you'll see more and more website names appearing. The encrypted content stays protected, but the destination often doesn't. To make this even clearer, let me jump over to the terminal for a second. I'll run a few DNS lookups using NSLOOKUP, GitHub, Wikipedia, and Ubuntu. Then I'll do the same thing again using dig. Both commands perform DNS lookups, just like your browser does in the background every time you visit a website. When we go back to Wireshark, those DNS requests show up immediately because that's exactly what these tools generate. So here's the takeaway. HTTPS does a great job protecting the contents of your connection, your passwords, your messages, the pages you read, but unless you're also using encrypted DNS, your network can still reveal where you're going. That's an important distinction. Encryption protects your data, but it doesn't always hide your destination. And understanding that difference is a big part of understanding how network traffic really works. The next time you see that little lock icon in your browser, remember, it protects the conversation. It doesn't always hide who you're talking to.